This is the first lecture on the theory of extensive measurement. You will recall in the previous lecture on the ordinal theory of measurement that we established that under certain conditions, namely that the ordering relation be a weak order and a certain other property, namely that there is a countable dense subset, there is a real valued representation of that weak ordering. The difficulty with this as a theory of measurement, and the reason why the theory is not complete at that point, is that the uniqueness of that representation is very weak indeed. It turns out that any strictly monotonic function of such a representation produces another equally acceptable representation. And this is unsatisfactory as far as the use of any strong mathematical techniques such as those in the calculus and more generally in analysis is concerned. The results would not, one would not, for instance, be able to, in a sensible way, talk about the derivative of a quantity such as distance with time if the only measurement of distance was an ordinal measurement. One needs something that is considerably stronger than that, either what is called ratio or interval scaling. And the whole point then of the rest of the theory of measurement is, in fact, to find structures that have a much more restricted representation. The basic notion in all such cases is that the representation has to contain information about the qualitative structure that goes beyond just the ordering relation itself. The first such system of measurement that played a role in physics and that was understood at an axiomatic level is the system known as extensive measurement, in which the added structure is an operation that will in general be called concatenation. And I will denote such an operation by the symbol little o, and it is going to be a mapping from pairs of the elements, the Cartesian product of A with itself, into A. An example of this is found, say, in the theory of mass measurement, in which we're dealing with equal arm balance, and we judge which of two weights is heavier by putting the objects on the pan balance and observing what happens. If the pan balance does not move, we say that they're equivalent as far as weight is concerned. If this one drops, so that the pan balance goes in that position, we say that A is heavier than B, and similarly if it goes the other way, we say B is heavier than A. Now, what we can do in this situation is, if we have a third object, let us suppose the balance had dropped this way, we could ask what happens now when we add a third object C to the right-hand pan, and I will denote that combining operation as B concatenated with C, and I can ask, is it the case that A is greater than B concatenated with C, or the same, or less than? And it is this added structure that we are going to try and deal with, and to see if there exists a set of reasonable conditions describing the behavior of this operation such that we get a much more unique representation. In particular, we're going to be looking for the representation in which the mass associated with the concatenation of two elements becomes the sum of the two masses themselves. The representation of the operation O will be into the numerical operation plus. That's the goal of the enterprise. All right, now let me begin to be a bit more formal about exactly what it is we want to prove. I'm going to begin with a non-empty set A, which is the empirical objects that we're dealing with, a binary relation on A that I'm denoting by this qualitative greater than or equal to, and that is, for example, in the case of the mass measurement, the ordering that is determined by the movement of the pan balance. And a closed binary operation of concatenation little o that is defined on A. Now what we're searching for are conditions under which a homomorphism exists from the qualitative structure, which I'll call script A, into the real numbers, positive real numbers, ordered by ordinary greater than or equal to and with an operation plus. That is, by a homomorphism, I mean something that takes the qualitative ordering into the numerical ordering and preserves it, which is given by this condition, for all A and B. If A is greater than or equal to B qualitatively, then it's equivalent to the numerical assignment to A being numerically greater than or equal to the numerical assignment to B. And the homomorphism takes the operation O, the concatenation, into plus, and that is formally stated in the second line, that the numerical assignment to A concatenated with B is the numerical assignment of A added to the numerical assignment of B. The question is, under what conditions does such a homomorphism exist? So you want the theorem to read if and only if, and then some conditions. Now I'll turn to a set of conditions that was arrived at by Roberts and myself in 1968. There's a long history, incidentally, of various theorems that provided sufficient conditions. Began with work by Helmholtz, and then Hölder, Suppies, and various others have contributed to the problem. The first condition, first axiom, is that we're dealing with a weak order. That is, the relation qualitative greater than or equal to is connected. That is, it's defined for every pair of elements, and it is transitive. That is a property just of the ordering. Our second property is a property just of the concatenation and the indifference part of the ordering, and it is known as weak associativity, and it's stated here. And what it's saying is that given three elements, A, B, and C, I can think of concatenating all three together, and it doesn't matter how I do the grouping. That is, I can concatenate B with C and find some object that's equivalent to that, and then concatenate that object with A. Or I can concatenate A with B, find something that is equivalent to it, and concatenate it with C. And that I will find that those two things are equivalent under the qualitative ordering. Now you can see that we know that if we have an order-preserving numerical representation, we know from the lecture on ordinal measurement that the qualitative ordering must be a weak order. There's no other alternative. Similarly, if we have a weak order for the qualitative relation, and therefore the indifference relation is an equivalence relation, that coupled with the additivity of the representation forces the weak associativity, and it does so for the following reason. We know from if x and y and z are numbers, associativity holds there. In fact, we normally omit the parentheses because it does not matter how we group addition. Now, if that's the case for addition, and if, in fact, addition preserves the operation, the associativity of the operation is necessarily forced. Another property that is also very well known of numbers that will also be forced is the commutativity of them, that it doesn't matter the order in which the addition takes place, and that would correspond in the qualitative system to the statement AOB is equivalent to BOA. That also is a necessary property, just as weak associativity is, weak commutativity is. However, it turns out, in the presence of the other axioms, this is deducible, and therefore we do not need to explicitly assume it, so that I will omit it from the list of properties. So far now we have a property that concerns only the ordering, a property that basically only concerns the concatenation. Our next property concerns an interlock between the two, and it's called monotonicity, and it is saying that if A is at least as large as B qualitatively, then adding the same element to both sides of the inequality does not change the order of the inequality. Whether I do it from the right or from the left, I get the same inequality. And you can see again that this is a necessary property for the following reason. Suppose I have a representation phi. Then A qualitatively greater than or equal to B is equivalent to phi of A numerically greater than or equal to phi of B. And now we know in the real numbers that if I add the same thing to both sides of an inequality, I don't change the direction of it. So in particular, if I add phi of C to both sides, the inequality remains the same. However, by the second property of the homomorphism, if it exists, this is equal to phi of A OC, and this is equal to phi of B OC. And therefore, because phi is order preserving, this is equivalent to AOC is qualitatively greater than BOC. So this is again a necessary property of the homomorphism if one exists. Our final property, or not, it's actually not the final one, it's the fourth one, is a property that is known as the Archimedean one. And it plays a role in this system that's analogous to that of the countable order dense subset in the ordinal system. And in fact, it is possible to show that under the presence of the other axioms, the Archimedean condition implies the existence of a countable order dense subset. However, many people feel that this is a slightly more intuitive property, and I will state it the axiom system in terms of this property. Let me begin by talking about what the Archimedean property of real numbers is. If I have real numbers x and y such that x is greater than y and both of them are greater than 0, the Archimedean property says that there exists an integer n. I'll use a positive integer n. I'll use I plus to stand for the set of all positive integers. There exists an integer n such that n copies of y, n times y, is greater than x. This is what we mean when we say that positive real numbers are commensurable. There are no two positive real numbers that are infinitely far apart. Is another way of intuitively describing what's involved in this property. Now, in order to impose analogous property in the qualitative structure, we have to worry about what we would mean by n copies of something. And that definition is given over here. It's an inductive definition of what I mean in the qualitative structure of n copies of A. One copy of A is A itself. Two copies of A is A concatenated with itself. Now, what that really means is that I am going to find an element A prime that is indifferent to A, and then I will combine A prime with A. But for short, we normally write that as A concatenated with A. 3A is A concatenated with A, then concatenated again. Now, by weak associativity, we know it doesn't matter how we put the brackets, but I'll write it in this fashion for reasons that will become apparent later. And this is the same as 2A concatenated with A. And in general, NA is n minus 1 copies of A concatenated with A. So there's no problem in qualitatively defining the analog of n copies of Y. In the present system, however, there is a difficulty in this condition of positivity, although once we get to the fifth property, that will be automatically ensured. And that would suggest then that the natural definition in the presence of positivity is to say that if A is larger than B, then there exists an n in I plus such that NB is greater than A. However, it turns out this is not quite strong enough. We need a slightly stronger property, which in the numerical system simply derives from the ordinary Archimedean property, but in the qualitative system it does not, and so I need to state it explicitly. The property can be described in the following way. Suppose I have numbers x, y, and u, v, and x is greater than y. Then the assertion is that there exists an integer n such that nx added to u is greater than ny added to the v. Or rewriting it, it says that n times x minus y is greater than v minus u. Now we see that in the case this number is positive, we know that because we've assumed x is greater than y. If in fact this is negative, there's no problem. Indeed, as long as this number, as long as x minus y is greater than v minus u, the property holds. If, on the other hand, v minus u is greater than x minus y, and that's positive, then by the ordinary Archimedean property, we know that such an n exists. It's in the analog of this version of the Archimedean property, the one that involves looking really at differences, is the one we'll impose here. And I've stated it here. It says that if A is greater than B, and C and D are any other two elements, then there exists an n such that n copies of A concatenated with C is at least as great as n copies of B concatenated with D. And the final property is positivity. It simply says that when A is concatenated with something else, the resultant is strictly larger than A itself. I want to say a few more words about the Archimedean property. It's different from the others in that no finite set of data would ever cause me to reject that property. Finite sets of data can cause me to reject any of the other properties. For instance, I can find a violation of transitivity simply by producing three elements that violate it. I could find a violation of weak associativity, again using just three elements, and a violation of monotonicity just using three. However, for the Archimedean property, it's an assertion that is inherently infinite in character, and no finite set of data would ever cause me to reject it. So that it is not a testable axiom in the same sense that the others are testable. And one clearly wonders what would happen if you delete this from the system. Now, it turns out that this has been studied by various people, and it is discussed some in the Foundations of Measurement. Basically, you have to make the domain into which you are mapping the structures more complicated than the real numbers. In fact, the kind of system that has been developed is called the non-standard reals. And one can develop the whole theory into the non-standard reals. However, it's considerably more complex, and little that is new really is uncovered in this fashion. So we will, in these lectures, simply always impose an Archimedean condition in order to maintain ourselves in the real number system. The theorem now that Roberts and I proved is that these 5 conditions are necessary and sufficient for the existence of a homomorphism from the qualitative structure into the positive additive reals. Moreover, the uniqueness properties are far more restrictive than in the ordinal case. In particular, the uniqueness theorem reads as follows. If there are 2 homomorphisms into the positive additive reals, call them phi and phi prime, they will be related to one another by a simple multiplicative transformation. That is, there will be a positive real number alpha such that for every element in A, phi prime of A is phi of A times alpha. When homomorphisms are related in that fashion by what's known as a similarity transformation, the whole structure is described as a ratio scale. This is terminology that was introduced by S.S. Stevens, and we will use it. This is a very strong form of uniqueness. It means, in essence, that once I specify the numerical value of a single element, for instance, if I specify that a particular element will have the numerical value 1, then the homomorphism is uniquely determined. There are no other degrees of freedom. And that is sufficient for the use of the methods of analysis. Scales that are invariant under similarity transformations will cause no problems in defining such notions as derivative and integral. A question that one always has to ask about any axiom system like this is whether the axioms are consistent with one another, which is demonstrated simply by finding some real structure that satisfies them. And that, in this case, is completely trivial, because we know that the reals under greater than or equal to and plus satisfy the axiom. So they're consistent. The second question that you are always interested in is there a redundancy in the axiom system? That is, can one of the axioms be derived from the remainder? And if they are not redundant, this is demonstrated by providing an example for each of the axioms in which that axiom fails and all the others are satisfied. Examples of this character are provided in the Foundations of Measurement on page 79. However, there is an error in those examples. Number 3, the one that is supposed to show just a violation of monotonicity, is incorrect and should be replaced by the following example. Let A be the Cartesian product of the positive integers with itself. Define concatenation to be component-wise addition, and define the ordering to be that is obtained by taking the product of the 2 components on each side and letting ordinary arithmetic greater than or equal to determine it. Now you can see that this fails monotonicity. For example, if I take the pair 3, 3 and compare it with 2, 4, The product is 9 here and 8 here, so the ordering goes in that direction. If I concatenate it with the pair 3, 1, then I get 3 plus 3 times 3 plus 1 is 24 on the left side, and 2 plus 3 times 4 plus 1, which is 25 on the right side, which reverses the ordering. It therefore fails monotonicity and in fact satisfies all of the other axioms. A question that has to be considered in connection with uniqueness issues is the possibility of using a representation into the real numbers where the mapping goes into some other operation than plus. The most familiar example of that is our representations into the positive reals with multiplication rather than addition as the operation. And you can see that if I have a representation phi that takes O into plus, and if I look at the exponential of phi, then that will take O into multiplication. It will also be order preserving, and it provides another perfectly satisfactory representation. There is nothing empirical that will decide whether you should be using plus or multiplication. Presumably, there are other equally valid representations. And the question is to describe the entire family of all these alternative representations and to ask, really, is there any preferred member of that family? This is done over here. Let f be any strictly increasing function that takes the positive reals onto the positive reals. I actually mean into. Define an operation that I'll call circle plus on the positive reals in the following fashion. For all x and y in the positive reals, x plus circle y is given by taking f of x and adding it to f of y and then computing the inverse of that quantity. And the theorem is that phi is a homomorphism of A into the additive reals if and only if psi, which is equal to first computing phi and then the inverse of f, this is function composition here, is a homomorphism of A into the reals under greater than or equal to and the operation circle plus. Moreover, if phi prime is another circle plus homomorphism, I'm sorry, not phi prime, psi prime is another circle plus homomorphism, that will be true if and only if there is a positive constant such that psi prime is obtained from psi by applying the function f inverse alpha f. Or actually the computation is the other direction. You first compute f, then multiply it by alpha, and then take the inverse. So that the structure of the equivalent homomorphisms in this same operation is a one-parameter family of functions describable in this way. In the case of addition, of course, that one-parameter family is just multiplications by a constant. All of these are equally valid representations, and there is nothing to decide among them other than convenience. And because of the familiarity of ordinary addition, that is very commonly used. We'll see some examples later where you can either use addition or multiplication, and in one case the physicists have opted to use multiplication rather than addition. This, in essence, completely closes the question of the uniqueness of the representation, and there's precious little of interest there beyond the fact that we are dealing, in the case of the additive homomorphism, we're dealing with a ratio scale. Having stated the representation theorem for closed extensive structure, there are two further things I'd like to do in this lecture, and they're closely related. One is to ask the question of how to prove the theorem, and the other is how to construct the numerical representation. We're not planning in these lectures to give proofs in full detail. They are in the foundations of measurement. On the other hand, it is, I think, sometimes helpful to have a bit of a guide to the general nature of a proof and to try and understand some of the structure that's involved, and that's what I intend to do for this theorem. The technique of proof is to reduce the theorem to another theorem. It is a classic theorem that arose in the study of measurement, but that has much wider use in mathematics. It's a theorem due to Holder, and I want to first describe that theorem and outline the nature of its proof, and then in the next lecture show how one applies that result to the proof of the closed extensive structures. Then, following that, I will consider a weakening of the axioms of the closed extensive structure to make them somewhat more realistic and useful in other contexts. So we turn now to the question of Holder's theorem, which is concerned with a structure that on the face of it looks fairly close to what we've been talking about. Will involve a set, a binary relation, but notice that I've written it slightly differently, and you'll see why in a moment, and an operation O, which will be a closed operation. I will say that such a structure is an Archimedean ordered group if the following conditions are met. First, that the operation on the structure is a group operation. That is, it has the following properties. O is associative. We recall what that is, that AOB concatenated with C is the same. Now it's going to be equality. I really mean strictly associative, as A concatenated with BOC. The second property is that there's a special element in A called the identity, and I'll denote it by E, that has the property that when it's concatenated with any element on either side, it simply reproduces that element. And the third group property is the existence for every element of an inverse element, which is denoted A to the minus 1. And the inverse element has the property that when it is concatenated with the given element, A, on either side, it produces the identity. You're familiar with various well-known groups. The additive reals form a group. The additive rationals form a group. In those cases, 0 is the identity. The multiplicative positive reals form a group, in which case the identity is 1. The second property of an Archimedean ordered group is that the set under the binary relation is a simple order. You recall a simple order is the same as a weak order. It's connected and transitive, but it has the additional property that if A is greater than or equal to B and B is greater than or equal to A qualitatively, that means that A is actually strictly the same as B. It equals B, not that it's indifferent to B. The third property is monotonicity, and that's essentially unchanged from the extensive structure. A is greater than or equal to B if and only AOC is greater than or equal to BOC. And similarly, on the other side, and I see I made a mistake here, it should read COB. The fourth property is the Archimedean property, and in this structure it's stated in the simplest possible way. You take an element A larger than B, and both of them larger than the identity. The assertion is there is an integer, positive integer, such that n copies of B exceeds A. Those are the properties of an Archimedean ordered group. And Holder's theorem, which is stated as theorem 2.5 in the foundations of measurement, is that every Archimedean ordered group is isomorphic. That is, there's a one-to-one homomorphism onto a subgroup of the additive real numbers. In other words, the class of all Archimedean ordered groups is not different from the class of all subgroups of the additive real numbers. Now I want to describe the general ideas that enter into a proof of Holder's theorem. The proof, incidentally, that is given in Chapter 2 rests on the theorem the proof that's given there of a theorem that we will be talking about in the next lecture. The proof that I'm going to outline here is a more direct proof, but essentially uses similar ideas. Let me denote by the symbol A plus the set of all elements in the Archimedean ordered group that are greater than the identity. I'm going to have to divide the proof into two parts, and this is very characteristic of the theory of measurement, that one runs into this repeatedly. And it depends on whether the set A plus does or doesn't have a minimal element. Now, to be concrete about this, again, think about the real numbers. The set of positive integers, for instance, does have a minimal element, namely 1. The set of positive rational numbers, however, does not have any minimal element. Given any rational greater than 0, there's a rational between it and 0. If A plus has a minimal element, let it be denoted as A sub 1. And now consider any other element B in A plus. We know that if B is distinct from A1, B must be greater than A1. And so by the Archimedean axiom, we know that we can exceed B with some number of copies of A1. And what I want to do here is pick the smallest number that exceeds it. That is, I want to choose n so that n copies of A do not exceed B, but one more copy does. And then I choose C to be an element that is formed from B by taking the inverse of n copies of A1. Now what I'm going to do at this point is establish that C has to be the identity element, in which case B has to be exactly equal to n copies of A1. That is, what we will be showing is that in the case that A plus has a minimal element, every element in B is an integral set of copies of that minimal element. Well, so to do that, I will consider the two other alternatives and show they're wrong. I will consider the possibility that C is smaller than the identity, and then I'll consider the possibility that C is greater than the identity, and get into trouble both ways. So let's first consider that E is, in fact, larger than C. Since E is the identity, n copies of A1 concatenated with E is just the same as n copies of A1. But E is greater than C, so by the monotonicity property, this has got to be greater than C concatenated with n copies of A1. But now for C, I want to replace it by what it's equal to, namely B concatenated with n copies of A1 inverse. And I put that in, and the monotonicity property justifies doing that. Then associativity justifies in changing the brackets from here to here. I've kept the order of everything the same. But we know that by the definition of the inverse, this has got to be the identity, and therefore this is equal to B. And the conclusion then of this string using the transitivity of the ordering relation is that NA1 is strictly greater than B. But that's contrary to my choice of N. Now we consider the other possibility, namely that C is strictly greater than the identity. That means C is a positive element, and therefore in the set A+, that set has a minimal element A1, thus C must be at least as great as A1. Note that by the definition of C, C concatenated with n copies of A1 running through the associativity argument is actually B. So I write that in the other order here, then use the fact that C is greater than or equal to A1 and monotonicity to substitute A1 in here and keep this inequality. And that is n plus 1 copies of A1 using the associativity to get from here to there. But that is contradictory once again to the choice of n where we had that n plus 1 copies of A1 is actually strictly greater than B, and this inequality goes the other way. So the two contradictions rule out those two possibilities, leaving only the possibility that C equals E, from which it follows immediately that B is equal to n copies of A1. We then define the numerical scale to be phi of B equals n for B a positive element and B equaling n copies of A1, 0 if B is the identity, and minus n if B is less than E, where n is defined to be the number of copies of A1 that is equal to B inverse. It is easy to show from this and the definition, well, let me actually show it, that B concatenated with B inverse through monotonicity has to be E concatenated with B inverse, but by the property of the identity, this is equal to B inverse. So, and this, of course, is equal to E. So B inverse is strictly greater than E, so this makes sense here. And then one has to go and prove that this is, in fact, additive and order preserving, which is fairly straightforward in this case, and I will not work out the details here. The second possibility, which is the more interesting one, is that A plus has no minimal element. I'm still going to choose a particular element and call it A1, and I'll choose a positive element, and this is going to, in essence, serve as the element to which I'm going to assign the value, a fixed value, in particular 1 as a possible value. And I'm going to measure everything relative to A1. In particular, let A be an arbitrary element of A plus. Then by the Archimedean axiom, we can make the following construction. Consider n copies of A. N is any fixed integer at the moment. So I construct n copies of A, and then by the Archimedean axiom, I can find some integer which will depend both on n and A, such that m of n and A, that is, it's an integer that depends on n and A, plus 1 copies of A1 exceeds that, but only m copies of A1 does not exceed it. So we bound this by this number of copies on the right and on the left-hand side, and this on the right-hand side. Now, what we're doing here is asking how well we can approximate n copies of A by copies of A1. You notice that if the representation exists, if there is an additive representation, then one is able to show that this is going to be equivalent in that representation to mn. Let me suppress the arguments of m and just write m phi of a1 has to be greater than n phi of a greater than or equal to, I'm sorry, this is n plus 1 over here, m phi a1. And so what we've got is an approximation. If I rewrite this, I can divide through by n and by phi of a1, so I get m plus 1 over n is greater than or equal to phi of a over phi of a1 greater than or equal to m over n. So there is here an approximate estimate of phi of a in terms of phi of a1. This is an arbitrary constant that we can pick, and we're saying that we know that this within an error of 1 over n is equal to m over n. Now, if we let n become very large, and if the limit of m that depends both on n and a divided by n exists, then that limit will be an estimate of phi of a divided by phi of a1. So the main problem in the proof is to establish that that limit actually exists. And that argument is worked out in detail in the proof given in Chapter 2. Now notice that at this part of the proof we have provided a constructive method for approximating the numerical scale. We've said that the way to go about it is to make identical copies of the element in question and then bracket it by whatever our standard element is, and that this will give us an accuracy of estimate that is good up to 1 over n, so that if we want accuracy of 1 part in 100, we must choose n to be 100. If we want 1 in 1,000, we choose n to be 1,000, and so on. The additivity follows rather immediately on the assumption that the limit exists. Let me sketch the argument. For the concatenation of AOB, we have this bound, which is the same kind of bound that we've been looking at. And then for A and B separately, or n copies of A and n copies of B separately, we have these equations. Now notice that the latter two equations, using monotonicity, we can in essence add them up, and we find then that, I've lost an A1 here, that we're getting this quantity plus 2 has to exceed NA concatenated with NB, and then the sum of these two quantities times A1 are a bound on the other side, and that's less greater than or equal to. Now, if we knew that this was equal to n AOB, we'd be in good shape. And to prove that requires knowing that the operation O is commutative. Let me illustrate why commutativity enters here. Let me take the case n equals 2. Then you have 2A concatenated with 2B, which is equal to AOA concatenated with BOB. And on the other hand, 2 copies of AOB is AOB, O, AOB. Now we're free to essentially to get rid of the parentheses by associativity. So this is really can be written in that fashion, and this can be written in this fashion. But those are not equal unless we know we can interchange the order. If we can do that, then it's easy to see that they're equal, and by induction you can generalize it. So the next part of the proof, which can be found in page 78, is to show that O is actually a commutative operation. Once that has been established, then you see we know that this equality is satisfied. We know that this is a tight bound on this quantity. This bound here may be looser than that. Therefore, this quantity here, this number, has to be at least as large as this one, whereas this number has to be less than or equal to this one. I've written that down here as these two inequalities. Now, if I divide through by n, so there's an n here, 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 and here, here, and here, and then take the limit. If the limit exists, and let me choose phi of a1 to be equal to 1, so that drops away, then this quantity goes to phi of a, this one goes to phi of b, 2 over n as n goes to infinity goes to 0, this goes to phi of a ob, this goes to 0, that goes to phi a ob, and this is greater than or equal to this quantity, which goes to phi of a, and this goes to phi of b. So I have an inequality that has the same thing on both sides, and therefore it's an equality, which proves the additivity. The system then generalizes to the negative part simply because the inverse is positive, and one sets phi of a, in that case, equal minus phi of a inverse, and that, in essence, gives the main steps of the proof. Now, I've omitted two key things: proving that O is commutative and proving that this limit exists. Those, as I said, can be found in the foundations of measurement. Now, in the next lecture, I will show how, in principle, you use this theorem, which is a very important theorem that will play a role at various times in our work, how you use this theorem to prove that a closed extensive structure has an additive representation.